Hi again, people. We're going to be continuing our discussion of differential equations. Now we'll be talking about separable equations, or separation of variables, and then we'll talk about slope fields. Wow, yay! I hate slope fields. Anyway, but separable equations is very nice. So, separable equations. Thus far, we have discussed two types of differential equations we can solve. Differential equations, where you have dy dx written into, there's a function in terms of x on the other side. And of course, you can integrate this as per usual. You just integrate both sides with respect to x. And then we've also discussed where dy dx is written in terms of a function in y. And then again, we take the reciprocal and then we integrate with respect to y. And then we just have to rearrange the equations such that we can get it as y equals. Well, what we'll be doing now is dealing with equations or dealing with differential equations where they're written in this form. dy dx equals f of x times g of y. Okay, this is the extent of our differential skills we'll have to be worrying about. Okay, so don't worry, nothing to stress about. But what do we have to sort of do in these cases? Whenever you have dy on dx equals a function in terms of x times a function in terms of y, it's important to be able to separate the two functions. If you can clearly get it as one function times another, there's no sort of lingering x's with the y's, then you can divide both sides by g of y, and we get to this next step. So we get 1 on g of y times dy on dx equals a function in x. Now, all I'm going to do is integrate both sides with respect to x. Okay? This dx and that dx cancels, and what we get on the left-hand side is the integral of the reciprocal of g of y with respect to y, and then we get the integral of f of x with respect to x. Both of the left-hand side and right-hand side can be solved. Isn't that kind of sick? Like, that's so cool. So, this only works if you can separate them. And when you need to ensure it's a product, okay, you can't do the same method for something like dy dx equals x plus y. Yes, they're two separate terms, but it doesn't work like this, okay? Because yes, it doesn't work. There's many other sort of issues with solving something like this, okay? So we won't concern ourselves with that. What you can, of course, do is actually solve a different type, just something like dy dx equals xy. So x times y. Let's do this. So let's use our separation of variables technique to be able to solve this differential. I want to get my function in y on the left-hand side. So I'm going to divide this side by y, and I'm going to put the 1 on y there. Perfect. My next line is 1 on y. Dy dx equals x. And then integrating both sides with respect to x cancels off these dx's. And now I'm just integrating 1 on y with respect to y. The integral of 1 on y with respect to y is just ln of the absolute of y. And then this is a half of x squared plus c. Okay. We need x as the, we need y as the subject rather. So we write this as y equals e to the power of a half of x squared plus c. And let me just write this in a different form, e to the c times e to the half x squared. And then this new thing here can just be a. So it's a e to the half x squared. Not bad, right? Yeah, that's the premise. How about this question? dy, we'll say solve, and I want you to have a go at it on your own. Solve dy on dx equals, and let's do x plus y over x plus 1 over y. Confirm first that this is separable. If this isn't separable, we are stuck. Okay, nice. Have a go. Now that you've had a go, let's do this. Multiply by y, multiply by y. This becomes the integral of y dy. Oops, we won't write that just yet. And then integrate with respect to x, integrate with respect to x, boom, boom. This is a half of y squared. And then this is x squared over 2 plus x plus c. Multiply both sides by 2, we get y squared equals x squared plus 2x plus 2c. Now I have a question for you. If c is a constant, 2c is also a constant. So what's the point in writing it as 2c? Just write it as c. And then y is the square root and plus or minus. We have to write it as plus or minus just because we don't know maybe if there's a restriction that they haven't imposed on this question. Okay, like I didn't write any restriction, but that's that. Nice. I'll get you to do a few more. This time, possibly they're going to have some initial conditions. Remember, you always need to get y as the subject in the end. Okay, crop out some of my working. Find the solution where y equals 0, y of 0 equals 1, and dy on dx equals xy squared. Keep in mind, y of 0 equals 1. That means x equals 0, y equals 1. Like, you know how we write f of x? We can also write y of x equals, and then whatever the function is, which just we don't bother writing y of x because it's sort of implied. But yeah, okay, have a go. Now let me do. So dy on dx, this is going to be 1 on y squared equals x. Let's just multiply everything by 2. I don't multiply everything by 2. Okay, you know what? Yeah, 2c is just c, so who cares? Now, when x equals 0, y equals 1. So minus 1 equals 0 plus c. So c equals minus 1. Then we get minus 1 on y equals x squared minus 1. There we go. Not bad, not bad, not bad. There you go. Now, how about this next question? Let's a y in the denominator. Yep, have a go. I feel like you guys are probably going to be getting the hang of this by now, so that's good. All right, find the curve passing. Let me have a go at it now. Again, you can clearly see that this is separable. So it's going to be y plus 1 dy dx equals x plus 1. Boom, 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 boom. Just together. Passing through 1, 2. So every time you see a y, chuck a 2 in there. 2 squared is 4. plus 2 times 2 is 4 equals 1 plus 2 plus c. And that means that c equals 5. And therefore, y squared plus 2y equals x squared plus 2x plus c. Now, can anyone figure out what this may represent? Plus 5, my bad. I'm trying to think. I guess this sort of seems like it might be a hyperbola. Maybe this is beyond the topic, the course. So, okay. Anyway, I think this represents a hyperbola. I'm not too sure. You probably have to sketch it up on some differential. Sketch it up on Desmos or something. But yeah, there you go. That's that. If you need to get y as the subject, what you do is you complete the square on the left hand side. And this is just going to be y plus 1 all squared equals x squared plus 2x plus 6. And then to which you square root both sides, and you get y plus 1 equals plus or minus the square root of x squared plus 2x plus 6. And then you'll move that plus 1 to the other side and make it a minus 1. Nice. There you go. So that's separable equations. Okay, and now we can talk about slope fields. So I don't really like this part of the topic, but it is what it is. Well, slope fields come in kind of handy when you have differentials which are too hard to solve. Sometimes differentials aren't separable. Sometimes they're not just written in terms of x or in terms of y. They might be even, yeah, I guess non-separable is the main thing. Other ones, you have many other ways to solve them. But yeah, at the level that we're at, we won't be able to solve a lot of them. So we may employ the use of slope fields to help us kind of get a picture of what our function could look like. So here's an example of a slope field, and I'll just mark in some things about what exactly a slope field represents. So probably you can see it in the name. Slope fields, they represent the slopes / gradients at particular x and y values. Okay, so these tiny lines represent the gradients at those points. They don't tell us that the function actually lives goes through there. That's not the point of the slope field. It just tells us that in this sort of position, it is very steep. Okay, whereas maybe in this position it is horizontal. So anywhere along here is horizontal, and anywhere here has negative gradients. And as you move to the left, they get steeper in the negative. Okay, that's sort of the premise. And you're gonna remember this is a sketch. This sketches values of dy on dx. Okay, that's the idea behind this. Of course, there are many slope fields, and they kind of look very ugly. I think I'll show you one of them, and I'll then show you how we can actually derive what the slope field, what the equation comes from. So here's this. Okay, you can see here, it's a slope field. It represents, I guess, the gradients at particular points for some form of I don't want to say function, some relation. Okay, and what's the equation, or what's the differential? It's dy on dx equals minus x over y. Now we can solve this, and we can see how this slope field sort of makes sense. So dy on dx equals minus x over y. This is separable. So I'd like you to have a go at finding the solution to this. And once you have, get back to me. Now, yeah, I'll do this as well. So we get y dy on dx was minus x. And then just solving this, we get, see. So it seems like we have a circle, don't we? Circle. And if we come back to the slope field, we can see that no matter where our circle is, of course, the center is the origin. No matter where our circle, sort of like what the radius is, at these particular points, and I'll put this in pink, we can start to kind of map out what our curve would look like. Okay, and you can tell just by looking at the gradients that it's actually going to be a circle. Maybe you'll say, no, how do I tell? In that case, I'll explain further. Because each of these slopes, these are tiny lines just to show what the gradient is at that point. If you know a particular point where it lies, let's say it lies on the point 0, 5. We know it goes through this point here. What's the gradient of the tangent at that point? Well, apparently it's 0. So it looks sort of like that. Now, as you move left, what's happening to the gradients? What's happening to the gradients around here? They're getting, I guess you could say, like, are they getting steeper? Yeah, they are getting steeper and in the positive. Then as you sort of move this way, okay, maybe I'm going too far. You can see at this point, the gradient's still like that. Then it's kind of decreasing, then it's decreasing, 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 decreasing. And then what can you tell here? Is there any line? Whoopsie. Is there any line along the x-axis? No. Why would that be the case? Because if you look at the differential, as soon as you have y equals 0, you're undefined, which means you have a vertical gradient, right? Or you have a vertical line at that point, which is why there's nothing there. So it means here, it's sort of looking like that. And you can sort of follow and say, as you kind of map out the curve as you sort of go along, like I'm not saying this is the most accurate, but you can start to tell by just following the gradients and saying, yeah, at each of these points, it's going to sort of line up with it, not line up completely, but match what the gradient is at that point because they're all tangents. Then you start to see that it's a circle. Okay. Particularly because it's horizontal, and the fact that there's no lines which represent gradients means that it's vertical. Okay. So that's the premise. Now, you have to be able to do these questions yourself. I really would hate if they did this to you in an exam, but they very well could. They could ask you to fill out a table like this and then map out what the slopes would look like on a diagram here. I'll show you how this first one would work. What is it saying? Oh yeah, you can create the slope field yourself on Desmos. Just search up Desmos slope field generator or whatever, and it should pop up. You can just do it on there as opposed to drawing it out. But I mean, in the off chance that they get you to draw it in the exam, I want you to have some practice. Okay. Nice. So let's draw out the slope field. Don't try and integrate this just yet. I know we all can, but let's draw out the slope field. You can see that this differential equation only is in terms of x. So it's going to make finding this, so putting in every number here a lot easier. So when x equals -3, what does dy dx equal? -6. So these are all -6. When x equals -2, what do these all equal? -4, -4, -4. When x equals -1, these all equal -2. I'm purely just subbing it into the dy dx equation. These are all zeros. These are all twos, fours, and then 6, 6, 6, 6, 6, 6. Nice. So if you're gonna do the slope field yourself, you have to go to each of these points. When x equals 1, or when x equals, let's say, 0, all of the gradients here are 0. So you're going to draw a little line just to show that the gradient would be flat there. At x equals 1, the gradients are 2. So, and we have to do 2, 4, and 6, so you might want to not make that super steep. Okay, you get the premise. I'm just going to finish this off and get back to you. Golly gosh, that took ages. So here's what I have. I hope you like it. Of course, if I really wanted to, if I was super Siebes, I would have added more lines. The more lines you add, the easier it is to see what the original function will look like. Now, I'm not going to because sack. Anyway, I think you can sort of tell. What does it say here? Important to note that since the derivative is a function of x, every slope matches the ones directly above and below it. Think of it as columns. Yeah, obviously, because the dy dx is independent of y, going up or down doesn't affect what the derivative is. There will be ones other, like in the future, where it will matter. In this case, it doesn't. So you can sort of tell, like, even if you start to go, dy dx, let's say I start here. Let's do this in pink. Let's make that pink. Yep. Let's say I start here. You can sort of tell that as you move to the left, like this gradient should sort of match. Now, no one's saying it's going to go through exactly those points, but maybe I've started in the worst position, but it could be somewhere there. And you can see it's getting steeper and steeper and steeper. And even on this side, steeper in the negative. Okay, doesn't have to go through exactly all of those points. The idea is that when it gets to there, it should be steeper. So as you move to the right, it gets steeper and steeper. As you move to the left, it gets steeper and steeper. Nice. That's the premise behind this. So by using calculus, find the solution to this dy dx. Can you see the possible solutions in your slope field above? Yeah, there are actually many. First of all, let's integrate this. I think we just can see that it's just x squared plus c. So wow, oh my gosh. Yeah, x squared, any function with x squared plus c always is flat at the x-axis. No, sorry, at the y-axis, because that's where its vertex is, and then it's just concave up. In fact, this pink line that I've drawn is one of an infinite number of solutions. Say I started here. As long as I'm sort of trying to match what the gradients are at these points, you can tell that there are an infinite number. Whoopsie. There are an infinite number of solutions. Nice. Yeah. Well, wonderful, wonderful. So let's do this next one. Complete the table below for the differential equation dy on dx equals -y and use it to complete the slope field. I would like you to have a go at this, please. Like, don't just scam me and not do it. Because there's only this and another one. So if you can get through this, then I won't ask of it any more of you. But I'm not doing it because I've already done this way too many times. So let me just copy in the answer. There we go. Got this off Desmos. So that's the slope field for this thingy. Since the derivative is a function of y, every slope matches the ones directly to its left or right. Think of it as the rows being all the same as, yeah, whatever. What it's saying is that because the dy dx is only in terms of y, the x value of the points make no difference as to its steepness or as to its gradient. Okay. And yeah. Now let's say that we wanted to go and draw in a possible line. What do you think this could possibly be? I mean, it's saying that as you're at the left, let's say we do one line here, you're super steep. As you move to the right, what's happening? Or rather, as you move down, not as you move to the right, what's happening? You're getting steeper, or you're getting less steep and less steep and less steep. Then you're approaching zero. That could be one. It could also look like this. Maybe that kind of atrociously matches the steepness. There you go, something like that. Let's see if I'm right. Is my little drawing here representative of dy dx equaling minus y? So this is a function in terms of y. So we're going to take that as 1 on y times dy dx equals minus 1. Integrating both sides. Integral of this is ln of y equals minus x plus c. And then y equals e to the minus x. And then e to the c is just a. So we have an exponential a e to the minus x. And I think you can sort of see that. Any negative x e to the power of a negative x in the any exponential with a negative power approaches like this. And the a, if it's positive, will mean it will be above the x-axis. And if the a is negative, it means it's below the x-axis. I hope you can sort of see that, right? As the y's get lower, the gradients start to get less steep. They start to approach zero. Okay, perfect. And what about this one here? Complete the table below. For this differential, dy dx equals xy. Have a go, have a go. I'm about to chuck mine in. There we go. Let's actually make this a bit bigger. I want you to sort of have a go at drawing this yourself. I'm very intrigued to see what people may get. Yeah, I guess what is this particular function here is in terms of both y and x, and therefore each of its positions are going to make a difference, right? It's not like it's going to stay consistent amongst all the x's or consistent amongst all the y's. Okay. Maybe you can actually solve this one as well. So I'm solving it off to the right just to make sure that you don't see it. Actually, I could also pause my screen, but I think I'm getting some exponential. Particularly, I think I'm getting this. Actually, I won't write it just yet. What have they said here? Notice that the slopes are positive in the first and third quadrants, negative in the second and fourth quadrants, 0 on the x-axis. So let's just choose a point and say that's where our function is. Because we can solve C for it. So let's say we're there. You can tell it's flat. What happens as you move to the right? You're getting steeper. What happens as you're moving to the left? You're getting steeper, but in the negative. This is all because I chose to start here. What if I chose to start somewhere here? Can we sort of see what happens? As you follow the lines, you start to get less and less steep, then you start to have positives. Like that. It depends. I don't know if this is a parabola or not, but it sort of looks parabolic. Actually, it's quite steep, so maybe it's not parabolic. We shall see. So solve this off to the side. Dy dx equals xy. Now, I was doing this. Integrating both sides, we get ln of the absolute of y equals a half of x squared plus c. And then here we get e to the power, whoops, y equals e to the power of a half x squared times e to the c, which is just a e to the half x squared. And you can see that in this example as well, it really does depend on the a to determine whether it's above the x-axis or below the x-axis. Very nice, very nice. Okay, what else is there? You could, I see a lot of these sorts of questions. They're multiple choice, and they say the slope field for a first order differential equation is shown. Which of the following could be the differential equation represented? So all of these are first order differential equations. We have to just determine which of these is the one that connects to this differential, this slope field. The best way to do this question is to give yourself some cases. Okay. Particularly, I don't know if you can see it this well, so I'll sack off all of the answers for a moment. And this here kind of follows a bit of a line. That line there, you probably can't tell, but actually maybe you can tell from here. Goes to the origin and it goes through 5, 5. That line there is y equals x. Now, along any point on the line y equals x, what is the gradient? The gradient is 0. Because what's the y value, what's the x value? They're equal. So it's like 5 minus, somehow they're canceling each other off. So if we look at our answers here, which of these is it definitely not? I think it's definitely not A, is it? Because it's saying the gradient at any point is the sum of the x and y values. I think it should be the gradient at any point should be the difference, because that subtraction is what's going to cancel it off and make it 0. So we already know it's not A, because think about the 0.55. It's saying you should have a gradient of 10, so it should be really steep, but clearly the gradient is 0. Okay, so now we've got to determine whether it's x minus y or y minus x. Well, if this is the line y equals x, think about any point above the function. Any point there. What can we say about any point here? Clearly, the y values are greater than the x values, aren't they? Because it's above the line y equals x, so y is greater than x. And what can you tell about the gradients? Are they positive or negative? I think they're all positive. So if the gradients are all positive when y is greater than x, should it be x minus y or should it be y minus x? I think it should be y minus x, because if this is a positive number, then it means the y values have to be higher than the x values. And you can also see it by, I guess, the opposite. When you're below the x-axis, that should not be blue on the inside, should be green. All of these gradients are negative. And they're all negative because the y values here are smaller than the x values. So if we look back here, if this is a smaller number than this, clearly this is going to be a negative. So we know that's the case. Nice. How about this question here? Which of the slope fields best illustrates dy on dx equals y on x? Have a go on your own, and then we can discuss. So once you've had a go on your own, let's figure out why one is the correct answer and one is incorrect. So it's saying here dy dx equals y on x. So I want you to think about the obvious things. First thing we can think about are quadrants. In this quadrant here, x is greater than 0, y is greater than 0. Here, x is less than 0, y is greater than 0. Here, x is less than 0, y is less than 0. And here, x is greater than 0, y is less than 0. So according to this dy dx, should it be positive or negative in the first quadrant? Well, if both x and y are positive, it should be positive gradients. What about in the second quadrant here? One's positive, one's negative, so it's going to be negative. This one here is going to be positive, and this one here is going to be negative. So maybe that's one trick. I don't know if it's going to be useful here, but that's one trick for us to be able to determine whether one answer is completely wrong, just because if it's multiplied or if they're being divided, one's not going to be, for example, if one of them here had negative slopes, then we'd say it's definitely not that. But in this case, I think both of them follow this little thing that we came up with. So that doesn't help. Another thing is you can say, well, what happens? Maybe instead of moving both left and right, or left, right, and up and down, just look at what happens as you move left or right. So as x gets bigger in this one, what's happening to the gradients? What's happening to the slopes? Looks like they're getting steeper, right? They're going from zero, steep, steeper, 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 even steeper. Does that does that sort of satisfy this? If x gets bigger, this gets steeper. I feel like if x gets bigger and the y's remain unchanged, because we're just moving horizontally, then the gradients should actually get smaller, right? Because my denominator is getting bigger. So I think it can't be b for that reason. Whereas if you look at a, it's, consider here, super steep. As you move to the right, it's getting less steep, less steep, less steep, less steep. And therefore, it's got to be a. What's another thing that you can check? What happens when x equals 0? All of these are vertical lines. That's because x equaling 0 here is undefined, and therefore the gradients are vertical. Whereas here, when x equals 0, the gradients are 0, which would have worked if it was x on y, but not in here. Nice. How about here? The slope field for a first order differential equation is shown. Which of the following could be the differential equation represented? Have a go, people. Okay, now that you've had a go, let's discuss. So I want you to think about one of the quadrants. Let's think about this first quadrant. The gradients are negative, aren't they? So here, negative gradients. So which of these dy dx's automatically can be cancelled off? Well, remember in this quadrant as well, let me just comment, x and y are greater than 0. So by looking at this equation here, shouldn't this give me positive gradients? Yes. So sack that one off. This one here, if x and y are both positive, and this stays positive, but you have a negative there. So that means this could be true. Again, here, this is the product of two positive numbers. How are you going to get a negative gradient here? So this one's going to be incorrect. And then D's got this extra negative. So therefore, it could be B or D. Now let's think about what's happening possibly when y equals 0. Actually, that's a good one. When y equals 0, what's happening on the line? Aren't all of the slopes horizontal? Which means dy dx should equal 0. At y equals 0, dy dx equals 0. And that's irrespective of what the x value is, right? Because it's across the entire line. If you look to this one, what happens when y equals 0? Doesn't this become undefined? And therefore, shouldn't it be vertical if b was true? Yes, it should be vertical, but it's not. So sack b off, and therefore it must be D. What is this? Oh, I think we did this one already, so we can ignore that. So use the slope field to draw. Oh, we did this as well. All right. Okay, this is a question that we would learn how to do. We have to learn how to do. So given the differential equation dy dx equals x minus y and the initial condition y of 0 equals 1, sketch the curve. Okay. So we have to somehow come up with a curve to solve dy dx equals x minus y. And it has to go through the point 0, 1. So let's first put in 0, 1 here. Actually, let's put it in pink. Now, I want you to just sort of have a feel about what's happening, okay? As I move to the left, what's happening to my gradients? they're clearly getting steeper and steeper and steeper and steeper, aren't they? What's happening as I move to the right? Now, granted, there is no horizontal line there, but there probably would be, I believe. Okay, okay, let's just see what's happening. I think it's going to look like that, and it's going to start to approach this because it's saying that any point there is going to have these same gradients. So it should look sort of like this. Okay. I think that's the case. Now you might say, Musa, how did I do this part? How do I know it does this? I think I just looked at it and saw that all the gradients were having to approach this particular line here because yeah, I don't know, I just got a feel for it, I guess. Like as I moved this way, it sort of directed me to keep going in the same direction. Each of these lines was sort of directing me to just keep going up. It wasn't like they directed me to keep going up and then one of them started doing this. And in that case, I would have turned around. You'll see that the more you do this, the more this sort of makes sense. Actually, there's a bit of a point. If you can sort of see this little line here, that's actually an asymptote. Okay. Now, can you solve this? I'd like you to have a go. I think I found it to be y equals e to the x plus c. Okay. Not that I actually know, maybe don't try and solve this. Maybe instead show that this is a solution to this because I think it's too hard. All right, how about this next one? Given the differential y squared minus 1 and y of 0 equals 0, sketch the curve. So seems like we're there. It says 0, 0. And what's happening? Like, okay, I feel like I don't have enough lines here. This is my issue. What I think I should do, because they've sort of just gone up by ones, I feel like I should be putting in maybe a half. What's happening at y equals a half and at y equals minus a half. So what's happening there and at y equals minus a half. When y equals a half, the gradients are a quarter minus 1, which is minus 3/4. So where here they're minus 1, minus 3/4 is going to be not as steep. Actually, yeah, let's put these in blue. Sometimes even I notice that I sort of need more lines to get an idea about what's happening. And what's happening at minus y equals minus a half, I think it's the same thing. If you sub in minus a half into there, it should be the same. So and the more lines you chuck in, so maybe if you do y equals 3/4 or something like this, you get a better idea. Because I'm starting here, I can sort of tell that as my y approaches 1, this starts to approach 0. So it's saving me from adding extra slopes. Because as y approaches 1, y squared goes closer to 1, and therefore it goes closer to 0. So this is what my function is going to look like. Okay. Perfect. If they told me some other condition, because this is one of many solutions, if they told me another condition, had they said, we'll say y of 0 equals minus 3, my curve would have looked very different. My curve might have looked something like, and it really depends on what these numbers are, but it would have looked a lot steeper. And I'm assuming that, okay, maybe we need to chuck in some more values, say minus 1.5. If we sub in minus 1.5 into this thingy, it's going to be what? 9/4. Where's my calculator? 9/4 minus 1. It's going to be 5/4. And is that going to be steeper or less steep? I think it's going to be less steep. So what you would have noticed is actually as you got closer, it would have started to have done something like this. So maybe that's what my other curve would have looked like. Okay, or maybe here it would have looked something like this. Or, and actually I should change this to another thing, just so it doesn't confuse. Let's make this light blue. And we'll say the light blue could be for y of 0 equals 2.5. Okay, these are all solutions to the differential. If they said y of 0 equals 1, then this would have been my line that I drew. That yellow line, because that's what satisfies it. So there's many, many answers to these questions, okay? But it just depends on what initial condition they've given you. Okay, I'll get you to have a go at this and then we'll come back to it in class, as well as this one. And I'll get you to have a go at some of these ones as well. And then that's the end of this part for differentials. We only have one final thing to do. All right, bye.